Okay, so Alex Grove is a product specialist from ALDEC. His title is Using FPGAs to Accelerate Verification of Your Next ASIC, Introducing the FPGA Co-emulator. Alex has extensive experience in design and verification of ASICs and FPGAs, as well as a broad knowledge of the EDA industry. Alex has worked for Synopsys, ARM's EDA business unit, Simplicity, Mentor Graphics, and is currently employed as an application specialist in First EDA. Alex is a solutions expert on the ALDEC line with a particular focus on a hardware-assisted verification RTL simulation product.
Thank you, Mike. So I'm last, so that has some benefits. That I've been listening to all the presentations ahead of me, and some things I'm going to talk about, we've already talked about. So we kicked off I think the first presentation from Synopsys this morning, that FPGA-based emulation was the future. So I'm more than happy with that, and obviously Andy Gardner talked about the use of FPGAs as well. So essentially my presentation and what I want to talk about today is using an FPGA as a functional verification platform. In my experience, actually maybe 12 years ago at Simplicity, was using FPGAs for ASIC prototyping, which is one use case. What I'm going to be talking about today is the use of an FPGA for functional verification. So to start things, I think if you look for the last 5 years, there's been somewhat of a renaissance in emulation. I mean, emulation is as old as EDA itself. Over the last 5 years, there's been an awful lot in the area of hardware-assisted, acceleration, co-emulation, emulation. And I came up with, essentially, I think there's 5 reasons why that might be. It's a somewhat tradition to start with Moore's Law, but Moore's Law has continued. I noticed actually when reviewing these slides that it's now actually been revised again. I think Intel on earnings call last year and now talk about Moore's Law slowing down to the doubling transistors every 2.5 years. But the simple fact is that things are just getting bigger and bigger, more complicated. Another aspect, and we talk about this at ALDEC with what we refer to as a hardware-dependent software. Software component has been increasing. Way back in 2009, the IBS talked about it, and then the ITRS. The amount of software you have in these systems and the SoC has exploded, and that's had a big impact to the costs, and certainly the hardware-dependent part of a hardware-dependent software is a considerable amount, and obviously that requires performance in order to perform those sorts of tests. Hopefully you would agree, that's what's brought you here today, that verification continues to get harder and harder. And obviously we can, Harry Foster's Mental Graphics have commissioned a survey now, the Wilson Research Group Functional Verification Study, rolls off the tongue. But you look at that, and there's been 4 studies now, and you can see quite clearly that verification has been consuming more and more of the project time. Unfortunately, actually, in the 2014 survey, the average was pretty much the same. But what you can see, looking at metrics like the number of verification engineers, the ratio of verification engineers versus design engineers, and also the number of projects where verification is greater than 70% of the project time. Is consistently growing. So hopefully you would agree. That's what brings you here today. That verification is certainly getting harder, or at the very least, it certainly isn't getting any easier. Then another aspect, thinking why is hardware assisted suddenly in vogue, and why is there more and more investment going into hardware assisted? So this is actually a slide from Chuck Moore, and I think he was from AMD or Intel. I can't remember. I should probably check that and put it back on the slide. Around about 2005, 2007, look at these benchmarks, the integer, single-threaded integer performance plateaued at best. In actual fact, we look at the benchmarks, and that performance actually degraded. And the reason this is important is your RTL simulator, this is how it works. This is the engine that the workhorse is behind an RTL simulator. So Moore's Law enabled us to reap many dividends over the years, but unfortunately another law that's not quite so fashionable, Dennard scaling, started to break down. And Dennard scaling states that as the transistors get smaller, the power density stays constant. And that started to break down around about 2005, 2007. And that essentially meant that we didn't get the benefits from a single thread performance, and that's one of the aspects why you now see a lot of multi-core activity. The trouble is with multi-core, they're not utilized in an RTL simulator. So the RTL simulation, the event-based, has been struggling to keep up with the requirements you put on it with your latest and greatest. And then finally, sort of a perfect storm now, there's also been the rise, and I hope you would agree with this, a rise of constrained random over the years. And obviously constrained random sort of started, I think, so I was actually with someone from National last week, I think it was 1992, so it's been around a long time, the idea of doing constrained random. But with standardization, UVM, Accelerator, and System Verilog, now it's widespread. Many people are using constrained random verification. And really for the context of today's talk, or my talk, you look at this as a very brute force approach. Obviously the reasons why you take this approach, writing directed tests is basically not practical, but it requires many verification cycles, which is obviously a great thing for acceleration. So, a simple verification platform, FPGA. So, I mean, I don't know how, who's familiar with using FPGA? It's been mentioned, very different. John talked about it for prototyping. Let's show our hands. Who's familiar with FPGAs for prototyping? So I think all ASICs have some way been proven with an FPGA, whether that's for the IP, doing some at-speed testing, or whether you've gone to the trouble of actually building a pre-silicon verification platform, maybe for the purpose of software. Well, what's great about FPGAs is they are always at the leading technology node. It has it translates to real business value to Xilinx and Altera's customers to be on the latest and greatest node. And obviously with Altera, they're now working with have our own foundry. And just to put that in context, and obviously this is a little bit outdated. Appreciate obviously Cadence now announced their latest system just in the last month or so. But put that in context, like Veloce 2 has a chip in it called Crystal 2, and that's at 65 nanometer. Whereas the comparables for things like, well, to be fair, the older devices such as the Vertex 7 at 28 nanometer, and now the latest and greatest is at 20, and now we have Autoscale Plus at 16 nanometer. So you always get the benefit with an FPGA that you'll be able to be on the latest and greatest technology node. Also with advances, and Xilinx had their stacked silicon internet technology, and that made a really big difference in the capability that you got from the FPGA, so how much capacity the largest devices had. FPGAs are really the only thing that can provide megahertz performance in terms of accuracy, and they will always be the closest thing you could ever get to your ASIC pre-silicon in terms of accuracy and performance. You get a fair amount of reuse, and with these sort of systems, typically you can take like a Lego approach where you can assemble the system for your needs. You can use the system in different forms as you go through the project. For example, you might be using smaller boards for IP development and then assemble those boards into a larger system for doing some full integration tests. But I think probably the most important thing, I think Andy Gardner talked about this, about scalability. It's a word that's used often. Well, we're talking about scalability, and you see that with the pictures of like the big box emulators, the enterprise verification. With an FPGA-based system, it is scalable in the sense that you can replicate these systems many times in a server farm, and that's primarily driven by the cost. The FPGA, because it's a generic platform that we take from Xilinx, in our case, actually most people's case it will be from Xilinx. It has a significant difference price point, and that's down to the fact it's a generic platform that's used for multiple things. And these are the numbers actually from Jim Hogan. He did an article in Deep Chip, and you can see there's from a sort of price per gate, which is a metric, is significant. So what is an FPGA co-emulator accelerator? Well, if you look at what an accelerator co-emulator is, there's 4 key components of what you need, and the first one is probably the thing that's most visible. So you need to have a hardware, you need to have compilers to get onto the hardware, runtime environments, and then verification IP. And the hardware is the most visible, and that's often the challenge I have, is that people see pictures of boards and they think FPGA prototyping. And the key thing about an FPGA-based system, it's an FPGA system that's been designed for the purpose of verification. And a lot of those capabilities are actually hidden from you. I mean, one example would be you need to communicate to a host workstation because you're going to be doing some form of acceleration with scheming. So you need to have a PCI endpoint. So you need to have that capability in your system and the appropriate IP. There's other aspects of things like emulation resources. So you have to have RAM in the context of emulation, where you have emulation models that you then map into that RAM. You need to have transceivers for doing pin multiplexing. And then most important, and this is probably the key difference between prototyping and using an FPGA for functional verification. It's used for functional verification because we're expecting to find bugs. So you need to have a fair amount of infrastructure in there to facilitate debug. Need compilers, and we have a product called DVM, which is a Design Verification Manager. So for an FPGA-based system, so there's pros and cons, but we get to leverage the fact that the tools come before the silicon, in actual fact, from Xilinx, which is very nice of them, and we basically build a mixture of custom compilers and vendor tools to enable you to map your design quickly onto that system. So it includes things like partitioning, automatic inter FPGA pin multiplexing, that sort of thing. But what's really important, and this is from the user's point of view, is that automated. So we try and keep the use model very much like a simulator with a script, and the way it's set up is that you're not going to have to get involved with what's going on. Mapping the design is, that's relatively straightforward. The hard thing, or if you've ever done anything with FPGAs, bring up and getting it actually alive and working. So you need a runtime environment. That's a key thing. There's a lot of IP that goes into that. Simple things like having a way of actually testing the emulation build before you map it to the system. And then another key aspect is when you compare to FPGA prototyping, with an FPGA-based co-emulator, it is an emulator in the sense that you have full control, so you can stop it. And that's a key difference to sort of FPGA prototyping that's running essentially free running. And because you've got full control, then you get full observability, so you can observe everything inside the emulator using, I think Andy was talking about a readback technique, which is a commonly used technique with Xilinx devices. And we do try, in our case, to try and give an RTL-like familiar environment to the hardware engineer. Then finally, and most importantly, in actual fact, because you wouldn't want to have to build this stuff all yourself, is you need verification IP. And this is just some of the things that ALDEC support, give you indications of the projects that we've been working with. And you need essentially transactors. And these transactors are for communicating from the emulator into, say, a system C test bench or UVM. Where it does get interesting from the FPGA side, and this is where it blurs, and we go into hybrid, you have things called speed adapters, and they're really basically FPGA prototyping, where you have devices that are running on the clock on the system opposed to the scheming clock. So and because you're using FPGAs, it's actually quite easy to have a mixture of FPGA prototyping and co-emulation. That might be quite interesting. To do this presentation 20 minutes is quite challenging, it requires discipline, especially with Mike. So now, strands of use cases. So this is actually something that we talked about. I talked about DVCOM. It's actually driven from working with one of our sort of lead customers. Really, very, very simple, and this is no different for if you're targeting a sort of big box emulator. Follow a coding style where you separate the timing behavior from your high-level description for your test bench. So that test bench is purely transactional. If you use a DPIC layer, which allows us to perform a cut, then you can then take that, what we would call the test harness, run that through our DVM software, and that will then generate a bunch of shared libraries and bit files, and then take that into your server room, submit it to a queue that's got one of our emulators attached to it, and you'll find that you'll then be running your UVM tests now, where the test harness is actually running on the FPGA co-emulator. And that's the sort of thing where one of our systems, where you could have 10 of those systems wrapped up in your server farm. And this is where we talk about this scalability that you get. Then another example, which actually I think Nick was talking about, you can do this with an FPGA-based system, and the reason you do that, again, with an FPGA-based system is the scalability, that it is something that you can have multiple copies of these systems for software development, and the situation would typically be you don't have all the pieces for your virtual prototype, your ARM fast model. Maybe you have a GPU or something, and you want to execute the two together. GPU is supplied as RTL, well, that would make perfect sense to put that on the Accelerator, co-emulator, and we integrate those two things together. And how you partition this up is obviously very dependent on the customer. And that gives you an indication of what that really looks like from the scheming specification. Essentially, you have certain behavior on the host workstation, and what we are implementing through the DVM software is all the scheming infrastructure to send those messages to and back from the FPGA system. So my sort of like, to summarise, sort of 10,000 foot view. If you look at the debug capability and then the runtime performance and scalability, then what we can see, and the way I would look at it, the big box emulator. So this is obviously from Cadence Old Palladium, from a great website actually, NVIDIA's sneak peek into their emulation lab, which is quite interesting if you're into this sort of thing. To the silicon. So obviously the big box emulator will have the greatest debug capability in terms of what you can do, observability, incremental turn time, but it's the least scalable and it's going to have the lowest performance. Whereas obviously the silicon is going to run the fastest and it's the most scalable. You can replicate that. But obviously if you've got a problem, it's going to be very difficult to debug it, and if you have a problem, it's probably a bit too late. The closest thing to the silicon would be classic FPGA prototyping, which has the benefit, it's not very easy to debug, but it has the benefit that's a reprogrammable platform, and you're doing it obviously with a pre-silicon development platform. And then really where else, what we're talking about when we're talking about FPGA co-emulation, and it really depends on the customer, it's somewhere between those two, where you're gaining some benefits, certainly in terms of scalability and what you can do in terms of debug capability. So what we've talked about very briefly is why I think acceleration is important. We talked about FPGAs as a functional verification platform, introduced what an FPGA co-emulator is, hopefully that was clear, and then we looked at two very common use cases of our systems, simulation acceleration for things like UVM, and then what we refer to as hybrid emulation, where we're linking into a virtual model, say an ARM fast model. So why FPGAs? Well, I think it really comes down to three things, and probably the first and last and most important is the performance that FPGAs bring. That's very key. They also bring a certain amount of reusability, but probably the most important thing, I hope you remember this, and Andy will talk about this in his presentation, is FPGAs give you the scalability that you can, through that performance and the fact you can replicate, will give you an unprecedented amount of sort of verification cycles, capacity for verifying these very, very complicated chips. So thank you very much. Hope you're on time.
Any questions for Alex before we go into the full panel? Any specific questions for Alex? Yep, Robin.
Robin Kennedy from KTN, and one-time employee at Altera. What's your view on the recent acquisition of Altera? Is this a risk to the use of FPGAs? There's one major player who is still in the market, but will they be there for years to come? And if Xilinx have it themselves, what's going on?
I don't know. I mean, we work closely with Xilinx, and from the sort of ASIC verification, Xilinx are very, very dominant in that space. You look at all the boards and people are doing it, working with Xilinx, and that generally down to the readback capability has a big impact. So I don't see it changing anything. If anything, it's probably a good thing for FPGA. It really, I'm passionate about FPGA, so it's like a good thing. In turn, endorsing what the FPGA company's been doing.
Okay. Yep.
Phil Chambers for Imagination. What kind of size design do you find to be a sweet spot for putting into this kind of system?
One that's not too big. Sweet spot. I mean, I think we're up to we have a whole range. And obviously, I suppose you're looking maybe at 500 million is then really at the top end of our systems gates. I think 620 we talk about. When we have the numbers, we always talk about 6-fin utilization. But it's a range. Obviously, the bigger the design, then the more complicated it is. But that's exactly the same on the big box emulators as well. So the performance, we've got more things to do in multiplexing. But we have customers who've done like